Hi, everybody. Just getting things set up so that we can take a look at our next lesson in our unit on quadratic functions. So we've been working our way through chapter 3 and chapter 4, and today what we're going to take a look at is section 4.3, which is using the process you've already learned of completing the square to solve an equation. So the objective is exactly what the title says. We want to make sure that you understand that there is another method that you can use to solve equations, quadratic equations, by using the method of completing the square. Some vocabulary to watch for as we go through this one. Please make sure you take a look for the term extraneous root and also exact roots. Now, as you are well aware, sometimes factoring is just not a practical way to solve a quadratic equation. In other words, you cannot factor. There's nothing you can do to factor. Now, in the past, at least in Math 11, what you learned was the quadratic formula. Well, we're going to take a look at another method that is very similar to the one that you used to change the standard form into the vertex form and see how that can actually be used to solve a quadratic equation. So it turns out that the vertex form is actually very easy to solve if you actually have your equation in the vertex form. It's actually just a few steps away from giving you the answer that you need. So it's very, very easy if you're careful and if you go in a certain direction, of course. So here is an example of a very simple vertex form of the quadratic equation. You can see that the vertex in this one would be positive 1 and negative 9. Now, first look at this, and I think without me saying anything more, chances are that what you'd be inclined to do would be to expand the x minus 1 squared by multiplying it all out and foiling it. And if you look at my solutions on the side, you'll see that that's what I did. I foiled it, and then I combined things. I looked for two numbers that multiplied to be negative 8, because that's negative 8 times 1, and added together to be 2. I found those two factors and then found my answer. Okay. Now, the way that I actually want you to try and look at it is from a different perspective. And that is, I want you to imagine that what you're trying to do is to isolate x. So you're going to start to move everything away from it. You move the negative 9 to the other side. And then you take the square root of both sides. You must simply remember, though, that the square root of 9 is both positive and negative 3. And then you simply have to move that 1 over. So that should be a negative 1. Sorry, guys. Just realized that when I saw it there. So this should be a negative 1 on the other side. So you would have negative 1 plus and minus 3. Negative 1 plus 3 will give you 2. And negative 1 minus 3 will give you negative 4. Sorry, my numbers are backwards because I did not shift that one. But you can see that your answers are exactly the same as what you found when you're factoring. Only at first glance, you can see that it's really quite simple, very straightforward. And that is, we have used the form of the equation when it is in the vertex form to solve it. And this one was a joke in some ways when they talk about it. Going ahead and foiling this and then factoring it is actually the long way. And the genius way is just simply to take the square root of both sides like that. So then, how can we rearrange the standard form into this form so that we can actually solve for our equation? Of course, the answer is we're going to complete the square. Just remember your purpose is to solve, and it's not to find the vertex anymore. You're going to have to work a little bit at trying to make sure you keep the two purposes straight from this method that we use, but they're very, very simple if you keep in mind your end goal. Okay, so here we are, and we're being asked to solve by completing the square, and here's our first equation. So now the first thing I did was, let me see, I actually brought the 10x over so that it was with the x squared, and I moved the number over to the right-hand side. Now what I'm going to do is set this one up to be a perfect square. So I take this and divide it by 2 and then square it. And I know that the number I need is 25. I'm going to add 25 to the left and to the right. This, of course, is the perfect square of x plus 5 squared, and this equals 46. Now I'm going to square root both sides, plus and minus the square root of 46, move my 5 over, and what I have, voila, are the answers for x, negative 5 plus and minus the square root of 46. So checking to see if these answers are really the x-intercepts or not, what I would encourage you to do is to take a calculator and calculate what is negative 5 plus the square root of 46 and what is negative 5 minus the square root of 46. I think what you will find is that it is indeed these two solutions. And what I've done is I've actually graphed this on decimals and checked to see what those points are, the positive one being 1.8 and the negative being negative 11.8. So this is indeed the way that we can solve an equation. Now, a couple of points. First of all, exact roots are not rounded. Those are the roots that you will see with the square root sign. They've not been put into a decimal to find an answer. Sorry, into a calculator to find a decimal answer. We simplify the square roots. We make them as reduced as we possibly can, but we do not touch the whole idea of turning them into a decimal. Now let's take a look at an example where a is not a 1, like this one. So what are we going to do when a is not a 1? Well, really, the only step that we have to add to that is that we're going to divide everything by the negative 2. So you'll see I actually kind of put an extra step in here, and a little bit later I slip into a faster way of doing it. Really, what would have made it faster is for me to simply divide everything by negative 2. So that would have meant I had x squared plus 3 over 2x, and the negative 7 over negative 2 would have turned into 7 over 2. Once you've got the 2 taken care of, then you find the number that completes the square. And if you look over here, 3 over 2 divided by 2 is 3 over 4. And then 3 over squared is 9. 3 over 4 squared is 9 over 16, which is what I'm going to add to both sides. So then the question is, where does this come from? So it's x plus 3 over 4 squared. And then I put these into common denominators. These negatives disappeared. Multiply the bottom and the top by an 8. So this would change to a 16, and this would change to a 56. And 56 plus 9 is 65. So now you're at the spot where you take the square root of both sides, and then you move your 3 over 4 over. You'd also ask yourself, is there a perfect square inside of 65? And there's not. And so I leave it in this way. The one thing I can do is that this 16, the square root of 16 is 4. So I can take that one out of the square root and just leave it simply in the numerator. So I have a 4 on the bottom. And you could write it as a common denominator. So just in case you're curious, the exact roots are negative 3 plus the square root of 65 over 4 and negative 3 minus the square root of 65 over 4. And then if I put those into the calculator and round them to the 2 decimal places, these are the numbers that I actually find for the roots. Now, just a couple of questions while we're at it to practice our applications of these particular quadratic functions. So the path of a kicked soccer ball can be approximated by the following function. X is the horizontal distance traveled, it's in meters, from the goal line. And h is the height in meters. Now, I noticed when I did this later that there was no h of x here. So imagine that there's h of x. Now, what they want us to find is to find the horizontal distance of the soccer ball from the goal line when it is kicked and express our answer to the nearest tenth. And then how far does the soccer ball travel before it hits the ground? So what we did was we actually completed the square again. So we took everything and divided it by negative 0.06 to get x squared by itself. It actually made the numbers a little nicer. Then we moved the 589 over to the other side, divided this by 2 and squared it, which gave us 696.96, which we added to both the left and the right. Then we figured out where it came from. X minus, and we're doing the square root of this guy to get this number, all squared. Simplified this, and then square root of both sides, and moved our 26.4 over. Now with this one, because we are looking for actual numbers, what we found was that the roots are approximately 16 and 36.8. So the ball is kicked. Basically, it's on the ground. It begins its projectile motion at about 16 meters in this scenario, and it comes back down again at 36.8. And so you could say that the ball travels approximately the difference between those two things, so 20.8 before it hits the ground. Next and last question is about a widescreen TV. It says a widescreen television has a diagonal measuring 42 inches. The width of the screen is 16 inches more than the height. Determine the dimensions of the screen. Okay, so here you have a diagram. It's 42 across the diagonal, the height, and then the height, or the length, I guess you could say, is the height plus 16. I think they called it the width in the text of the question. So that if we relate these three sides using the Pythagorean theorem, then this side squared plus this side squared equals 42 squared. And again, all I've done is gone ahead and expanded this and simplified it, moving everything around. I think I eventually factored out a 2, kept the number over on the side, found the number to complete the square, added it to both sides, simplified this to where it comes from, took the square root of both sides, and there you have it. You have your exact roots and the approximate roots. Now in this one, we get two answers, 20.6 and negative 36.6. Now, this is what we call an extraneous root because even though it is truly a root of this equation, in the context of our question, there's no such thing as negative length, so we say that it makes no sense. Okay, the height of the TV is about 20.6 inches. So just to clarify that once again, an answer obtained when we're solving an equation which doesn't satisfy the initial conditions, in other words, it doesn't make sense, is called an extraneous root. There you have it, solving equations by completing the square. Here's your homework. Make sure that you go through each one and that you've practiced them, bringing any questions you have to class. Good work, everybody.